Okay, let's do another example. We have a similar looking circuit with a slightly different configuration. Again, a couple resistors, an inductor, and a capacitor. I've labeled the inductor current and the capacitor voltage. And we have a switch here that closes at time t equals 0. Let's find the initial and the final conditions. Again, step 1. Let's go t equals 0 minus, such that we can assume we're in steady state conditions. Okay, redraw the circuit with the switch open. Inductor looks like a short circuit since we're in steady state and we only have DC sources. Capacitor looks like an open. 40 volts, 30 ohms. This is what we describe as I0 minus, and 50 ohms, and this is what we describe as V0 minus across the capacitor. Okay, so we see we can write an expression for I0 minus as being negative of the current supplied by this 40 volt source through the 80 ohm resistive path, just V equals IR, since 40 volts is across the 80 ohms. Note that the current is drawn in the opposite direction is what you would assume with passive sign convention. So that gives us negative half an amp. It's our initial condition. Note that this also means that I0 plus is going to be defined as negative half an amp. And that's because the inductor current can't change instantly with the switch, but we have to assume it's steady state in order to solve for it. And the voltage across the 50 ohm resistor can be found as a voltage divider, so that's going to be 40 volts times 50 ohms over the sum of the path, which is 30 plus 50, and that works out to be 25 volts. Likewise, V0 plus is going to be 25 volts. Okay, so next we look at the time going off to infinity, or at least long enough such that we can assume steady state. When the switch is closed, we're shorting out the 40 volt source and 30 ohm resistor. Inductor looks like a short, resistor, capacitor is an open. Note that there are no sources in this problem, therefore the final current has to go to 0 amps and the final voltage has to go to 0 volts in steady state. Okay, now to find the initial condition of the first derivatives of the current and voltage, we take the circuit at time 0 plus. Note that this is not steady state anymore, so we're in transient domain, so we have to leave the inductor and the capacitor in the problem. So switch shorted, goes to an inductor, to the 50 ohm resistor, which is connected in parallel to the capacitor of value 20 microfarad. So at time 0 minus, that is, the voltage will be given across that capacitor as V0 plus, which we know. The current through this inductor will be given as I0 plus, which we know. What we do not know are the first derivative terms. Remember, for finding the first derivative term for the inductor, we needed a KCL expression. So we're gonna, if we assume this bottom node as our ground, this top node becomes V0 plus, which is defined, but we're gonna do a KCL at V0 plus. The current through the inductor is given as I0 plus, it's a known. Current through the resistor, 50 ohm resistor, is V0 plus minus 0 over 50. That is also known. Then the current through the capacitor is given as C times the first derivative of the voltage across the capacitor, dV0 dt equals 0. So this is known, and C is known, so we can rearrange this and solve for dV dt, and that has to be 0 volts per second in this example. I believe that was also the case in our last example. It doesn't have to be, but it is in this case, and it was in the last example. It's always worth solving it out. I believe I might have misspoken and said that for finding the first derivative of the current through the inductor, we use KCL. It's finding the first derivative of the voltage across the capacitor where we need the KCL. In any case, you're going to do a KCL and a KVL in order to solve this out. And in order to find the first derivative of the current, we need the voltage across the inductor. So we're going to do KVL of the left mesh in this case. Noting that we can just describe that mesh current as I. So first, the voltage drop across the inductor is going to be given as the inductance times di dt. And then the voltage dropped across the 50 ohm resistor as being, well, we know it. And we know it as V0, and in this case it would be negative. So therefore we can describe di dt equals V at times 0 divided by L, which works out to be 10 amps per second.